that was having that issue. With all the other technical issues we've had, it's not as bad as last spring, thank goodness. It's still kind of rough, but it's not as bad as last spring. But just to kind of highlight those things there. Couple of things just to point out to everybody. We're in week 2. This is your link to the Vernier video analysis. So if you're doing your lab via Zoom, or you happen, over here in Tonkawa, you happen to miss for whatever reason yesterday's lab, Monday's lab, you can still do and get counted for your physical in-person lab. And remember, I've got to have 8 of those from everybody. So we've got to have 8 of them. And luckily, a lot of the labs are going to be pretty flexible, that we can accommodate if somebody has to be in quarantine, if somebody has a family emergency. I've got it pretty flexible, but I need for everybody to, because we will have what will essentially count for 12 in-person labs. And if you miss more, if it were a traditional semester, traditional everything, if you miss more than 4 labs, you get an F in the course. So that's why it's important that you get 8 of the hands-on labs completed. And Monday's lab is one, and for those of you over in Enid, Thursdays will be that. So the Vernier analysis software is there. The laboratory materials is under the laboratory materials. This is where you will turn in your laboratory report. And I have the recording of the 7:30 lab from Monday. Yeah.
I got on there to rewatch it, and the part where you're explaining the graphing is completely white.
The part that had the notes?
Yeah.
Yeah, that's why I thought it might, and that's where the notes are. Yeah, I thought it might be like that, and so I'm glad you watched it to let me know. And so we can tell everybody that when I went to the document camera, I was a little concerned that it wasn't recording. And so I do have the notes. So for those of you who are strictly Zoom or who are picking it back up, there are the pieces of the paper that have that go with that part.
Well, it was on the, like when you were on the screen too,
For Excel part?
Yeah, it's completely white too.
Huh. Because I shared my screen.
I
don't know. We may have to record it again on Thursday. I'll try it again with my class on tomorrow over in Enid. We'll give it another whirl. Because at my home computer, I've got it set up that I can record through Zoom, no problem. I can do all kinds of fun stuff, no problem. We'll try it over there to see if we can get it as well. But we're using Excel to do the graphing, and so for those of you who are Zoom, we've got time, because the lab's not due until September the 3rd, so we've got time to get it kind of caught up, and we want to make sure it's there, so. All right, I appreciate that, Madison, thank you. But, so those are, and if, in fact, for those of you guys that are Zoom, if you are available tomorrow at 10:30, go ahead and I'll send out a Zoom link and you guys can Zoom in for that startup lecture, if you're available at 10:30. That'll also possibly help us do that. I might actually Zoom in from my office computer, and that way we know it's going to be recorded that way. So I'll do another recording, and that will help for everybody. But if you want to see it via Zoom tomorrow at 10:30, I'll send out a Zoom link, and we'll do it that way. For the 10:30 lab over in Enid, we'll get it recorded again. Because I really want to use that stuff again about how to use a graph in Excel, because I think that's helpful for everybody. All right, so that's where that is. Blackboard assignments, you do have a weekly review. Easy points. Easy points, okay? Just remember that. And even though we didn't talk about it much last week, I do want to talk about it now. These are solution and example videos. We are about to cover Trig, and I have some historic Trig things. I also have a video on significant figures and conversion examples. I've got another link for help with Trig, and we will be using certain things in algebra over and over again, one of which is solving two equations with two unknowns. So here is some help for solving two equations with two unknowns. And if you ask, say, hey, I'm really having trouble with this particular homework problem, or I don't understand this example, and that's what you're putting in your weekly evaluation, that's what I use to create some of these. So, the more you guys ask about, the more of the helpful videos will actually come out and be there. So if you have a question or you're confused about something, check in the solutions and example videos folder. Your answer to your question might be there, because that's how these are all being developed. And just to go back and double check, because I don't remember what I have from the week one. I don't know if there's anything in there. Yeah, week one, there isn't anything in there. I couldn't remember. I have 3 classes, and I can't remember what's in which ones anymore. So, but you want to kind of keep track of those example videos. So any questions about logistics, what's due, what's not due? The WebAssign, just double check here. I did go in and do some cleanup in WebAssign. And these dates, at least for these first 3 homeworks, all of these dates are correct. Up through the homework for chapter 2 is correct. Dates are correct. All right, questions? We're going to dive in. Okay, so now we're going to... Everybody good over in Enid? Everybody good online? And let the computer have its way. Okay. Always love these coming in here. You have so much fun. Okay, so today we're going to start talking about trigonometry. And there's lots of trig. Okay? There's lots of trig out there. Basically, even though you guys probably haven't taken trig, I'm going to teach you everything you need to know to do this class, and we're going to work through it. So trigonometry is based off of a triangle. So let's start with the fact that we normally think of the world in Cartesian coordinates, where we have this is in the x direction, this is in the y direction, and we live in that spot. And this is fuzzy. Let's see if we can focus it a little better. That's better. That looks good on the screen. So we have Cartesian coordinates. And if I were to put a dot on my Cartesian coordinates, we remember from way back when that says that's an x and a y, right? We remember that. From somewhere along the line, we define that point on our Cartesian coordinates in terms of its x and its y value. Now, I can actually draw an arrow here to give us that point. We're going to give this arrow a special name. We're going to call that arrow a vector. And vectors are important because they have direction and magnitude. So if I'm thinking that I am traveling on a compass, this is north, south, east, and west. And for those of you who don't remember it, there is an acronym, never eat sour watermelons, right? So never eat sour watermelons. And that's why we can do that in terms of north, south, east, and west. And so the way I've drawn this vector, it's headed in the northeasterly direction, if I'm thinking about this as terms of cardinal points. So a vector has direction and magnitude. And when we start talking about physical quantities like displacement, velocity, forces, they're going to be vector quantities. They're going to have direction and magnitude. So we can look at this thing here, and the magnitude of that, we're going to call that R, and we're going to do that for an important reason. We're going to call that R. We know how to calculate the magnitude of this thing, right? We've done it. We've done it all along. We've done it like this, and we've used good old Pythagorean's theorem, a squared plus b squared is equal to c squared, or in this case, x squared plus y squared is equal to r squared. And so we can calculate the magnitude of this thing just by knowing this definition of points. We can do that. We've done it a lot. Now, if I am not in Cartesian coordinates, we have something that we call polar coordinates. It's a different way of looking at the world. And if I am flying an airplane, it's usually the way that I'm flying the airplane. I'm doing it in terms of those cardinal components, and we give this thing an angle, and we're going to call that angle theta. And I could describe this point not just as x and y, I can describe this point as r theta, and this is polar coordinates. And this is Cartesian. So it's just another way of representing things. However, if I'm using this theta, I can do something. And you've probably seen it before. We can use a mathematical fraction, call it the sine of the angle, and that is just going to be my y component divided by the hypotenuse. So sine of an angle is just a fraction. Sine goes from 0 to, or actually goes from -1 to +1. But it gives me an indication of where things are, and that's my mathematical interpretation, but it is just a fraction or a ratio. I can do the same thing for cosine. Cosine is another one. And in this case, it's x over r. And the other one that we end up using all the time is tangent over r, which is going to be y over r. So I can actually represent those things in terms of those components. Now, I'm going to tell you guys something. That's not how I remember everything. I remember it because I've done it enough. Well, let me give you a little bit of help. Okay? A little bit of help. So let's take my triangle. And this is when we have a right triangle. Now, there are trigonometric functions that don't care whether or not I have a right triangle or not. For the most part, for you guys, we're going to stick with right triangles. It's going to make life a little easier. And I'm going to define this is the angle theta, just like I did with my other right triangle. I'm going to do this as the hypotenuse of my triangle. This side of the triangle is next to or is part of my angle, right? So I'm going to call this one the adjacent. This side of my triangle is opposite of the angle, so I'm going to call that opposite. So now if I'm doing my sine and cosine, my sine of the angle is going to be the opposite over the hypotenuse. Cosine of the angle is going to be the adjacent over the hypotenuse. And tangent of the angle is going to be the opposite over the adjacent. Now your book is going to stick with the x and the y's. The reason that I utilize this one is when I am drawing a physical picture, my triangle may be like this. And if it's like that, the x and the y's don't necessarily make sense. My triangle may also be like this. Again, in that situation, the x and the y's don't necessarily make sense. And I'm trying to keep track of which side I need to put in to solve my problem may be a little different. But if I have it this way, I can always write down which one's the opposite, which one's the adjacent, and which one's the hypotenuse. Because one of the things in physics is we're always going to be changing our frame of reference. We're going to look at frames of reference. How am I interpreting something? What am I doing? Because we all know if I'm riding on a train and I'm walking to the back of the train car, if I'm writing how fast I'm walking to the back of the train car with respect to the train, that's going to be one value. If I'm walking on that train car with respect to the planet Earth, it's another value because the train's also moving. That's a frame of reference that we're going to be playing with. And physicists like inclined planes, so we're going to be doing a lot of inclined plane stuff. So by looking at and drawing your picture like this, it's really going to help you out, and it's going to start building your toolbox. One of the things I encourage you all to do is take a plain sheet of paper. And you're going to use that plain sheet of paper throughout the semester. So I would start doing it normally, historically, when we all took in-person tests. And we sat in the classroom and we did in-person tests. The instructor would let you say, you can bring in a cheat sheet, right? You're going to create your own formula sheet. So what I would do is I would do up here in my corner of my page, so I'd go ahead and I'd create my triangle, and I would write it as hypotenuse or R, and I'd write this as Y or opposite, and I'd have X and adjacent, have my angle, and they do my cosine the angle is going to be X over R, or adjacent over the hypotenuse. Sine of the angle is going to be my Y over R, or my opposite over the hypotenuse. And tangent of the angle is going to be Y over X, and that's going to be opposite over adjacent. And I've got that X squared plus Y squared is equal to R squared. So I have started my cheat sheet. Or for this case, you've got a reference sheet that when you're working the problems, I can always have my reference sheet right next to me and I'm working my problems. Now, if I want to find the angle, okay, I'm given at Y and I'm given X, and I want to find that angle, I'm going to do what they call that function, cosine to the minus 1 of X over R. That's going to give me the angle. And when I'm doing that on my calculator, see if I can get that without too much of a glare. I'm doing that on my calculator. I'm going to take it, for example, if I have this side is 2, whatever they are, 2 meters, 2 meters per second, whatever it is. This side is 2. We kind of know what that angle is going to be, don't we? If that side is 2 and that side is 2, this is a right triangle, we know that that angle is going to be 45 degrees. 2 squared plus 2 squared is 4 plus 4 is 8 squared, so I'm going to get the square root of 8, right? That's going to be 2.82. So if I want to come over here and do my cosine of my inverse cosine, I'm going to get 2 divided by 2.82. That's going to give me my angle. So I'm going to use the inverse cosine function on my calculator. I got 2 divided by 2.82. And it gives me, because I've used only 3 significant figures, it gives me 45 degrees. So this is how you're going to come back and go back and forth between the lengths and the angle and all of that lovely. So let's do a quick problem utilizing this. All right, so I've got a big tree here. And I've got a flat piece of ground here. And it turns out you can take your cell phone, okay? And you know what's coming. You know what's coming, folks. So just go, uh-oh, she's going to do it again. Just start this whole semester going to do it again. You're going to probably see an assignment that has to be done by Monday or Tuesday, probably by next Wednesday. Give you plenty of time to do it. That you're going to go outside and you're going to take a picture of something, a building, a tree, the fountain outside of the student union, over in Enid. Let's see, what's a good one over in Enid? Oh, you could use the planetarium over in Enid. Go outside and sight something, meaning go out and look at it. So here's my little person here. And you can take your cell phone, and there is an app on your cell phone that utilizes the camera that will sight the top of something. You use your camera and you sight the top of something. And that'll give you an angle. So we're going to say that this gives us an angle of about 20 degrees. Then you can kind of estimate the distance between the center of this tree and where you're standing. And we're going to go ahead and say for this it's going to be 30 meters. And we're also going to say that my cell phone that I'm sighting with is at 1 meter. Okay? I want to know how tall the tree is. I want to know how tall the tree is. Well, I'm given this length, right? I'm given that. I'm given the angle, even though if I'm drawing my picture, this is actually the triangle that I'm working with. There's my right triangle. So what I'm actually going to calculate is this right here. So I'm going to call that H prime. And so H is going to equal H prime plus 1 meter because my cell phone is 1 meter off the ground. So I've got that part. So let's do that. So if I've got that, we know that cosine is going to be the 30 meters divided by r, which is this right here. That's not going to help me. I don't know what r is because I don't know what h is. So cosine is not going to help me. Sine That says that's going to be my h prime divided by r. That one's not going to help me because I still don't know r. I don't know r. So it's like, okay, so neither one of those are going to help me. But my tangent, that's a different story. Tangent of the angle is going to help me because that is going to be h prime divided by my 30 meters. Woohoo! I have the angle, I got my 30 meters, and I'm going to be able to calculate h prime. So now I'm going to clean this up. I've got 30 meters times the tangent of 20 degrees is going to give me h prime. I'm going to plug that into my calculator. And that says my tree is 10.9 meters, but that's not my tree. I have to add the 1 meter to it. So that's my 10.9 meters plus my 1 meter. My tree is 11.9 meters tall. I can use the trigonometry to determine the height of my tree, or my building, or the fountain, or a variety of things. So there will be a real world problem that you'll have to do. And it'll show up in Blackboard in the assignments. And basically what I want you to do is give me your picture of what it is you're measuring. Give me the data that you used and do the calculation. And take a picture, so you're going to give me a piece of paper that's going to look something like this. And I think one of the homework problems does this as well. So when you're working any homework problem, any physics problem, any of my tests, when you're going to do the tests and the tests are online, I'm going to have you submit your work. I give partial credit. Even if it is a multiple choice question, I am going to give partial credit because you showed your work. So even if you get it wrong, if you show me your work where it makes sense, like for example, if I ask you on a test, what is it about a vector? What makes vectors special? They have direction and magnitude. There's really no work to show on that kind of a question. But a question like this, there is work to show. You will always get points for drawing your picture. Because drawing your picture is going to help you set up your problems. It's going to help you keep things straight. I worked through, on this case, which equation do I use? Because 9 times out of 10, somebody is going to tell me, I just don't know what equation to use. Well, part of the reason you don't know which equation to use is because you haven't written down your variables yet to tell me what you know and what it is you don't know. And when we get into our equations of motion, there are going to be 3 equations of motion. And which equation you use is based on what you're given. Because there's going to be multiple ways of solving the problem, but it's going to be based on what you're given. So writing down what you know and what you don't know helps. So that's kind of why I went through going through which one of these I didn't use, because I don't have all the information. Okay, there's a homework problem out there, very similar to that. We've got a hiker. And that hiker is going to go up to this mountain here. It's kind of like coming up to the Rockies, coming from eastern Colorado, coming up to the Rockies, and we want to know how tall they are. I can take my map. I can figure out where I'm at, right? We can find this distance. That's going to be distance x. We'll be able to measure this angle. Okay, that gives us an angle. This is what we're after. But in this case, we don't necessarily, go the whole way, but we can do this. We can drive a little ways, and we can measure another angle, and we can measure this distance. So we just figured out that h is going to be some distance times the tangent, right? So h is going to be, in one case, x, and I'm going to go ahead and give these subscripts so we know which angle we're working with. I got x is equal to the tangent 1, and I have h is equal to x minus d tangent 2. Two equations, two unknowns. I don't know x, and I don't know h. But I have two independent equations, so I can solve for x, or I can solve for h. Two equations, two unknowns. And so we can set up the problem to actually calculate it. I'm going to let you play with that because that's a homework problem. Couple of other things when you're looking at your textbook. Problem I gave with the tree is very similar to this example problem. So a good study guide for this chapter, and we'll get to all of it, and this is kind of one of those things we want to look at. Good study guides. Your study guide starts out with whatever the summary of the chapter is. One of the reasons why I don't write out study guides is because you already have a really good one. You can look at the summary of the chapter. Also, when you're working your homework problems, having the summary of the chapter open is probably a good idea because most of the equations that you're going to utilize are in the summary of the chapter. So the summary of the chapter is your first thing. The next thing is when we go through, so I've got chapter 1 out here. And we all know physics books. You could always tell the physics majors because their books were so dang heavy. My backpack is always filled with very heavy books between my notes and my physics books. Ugh. So when you go through your chapter, you can look at the highlights of each one, and it's got the makers and the building blocks, and it's got like the analysis of an equation. This one does the unit analysis. Then we got our significant figures. You've got an example for calculations. And they did brain cell estimates. And now we got our coordinate systems. But here's an example. And it's an example that I sort of did in class. This would be an example that I would go through and redo. You're likely to see something similar to it again, especially since you know there's at least one homework problem that's like that. If you've seen it as an example in class, there's an example of it in the textbook, and you've had a homework example that's like that, odds are you're probably going to see something similar to it on a test. Also, if you see it in a quiz, you're likely to see something similar to it on a test. So that's one of the reasons I don't do study guides. Also, this is kind of nice about how our book does it. You can cover up the solution. So you can actually rework the problem going through it and cover up the solution. So that's another really good study technique for these. Okay, so we talked about polar coordinates. We talked about one of the things I didn't talk about, and let's go ahead and do that so that we can make sure that everybody's kind of following along. In some cases, you're going to have to watch how the problem it talks about, okay? Because if I'm trying to find a vector in this quadrant over here, so we've got a vector that's in this quadrant, and this is x, and this is y. This is going to be minus x, and this is going to be minus y. Watch very carefully how WebAssign or how the problem is stated. Because when I calculate this, if I know minus x and I know minus y, and I go in and plug in my calculator and I look for the tangent of the angle, it's going to be minus x over minus y. That's going to give me an angle. This is the angle that I calculate. Okay? Everybody understand that that's the angle that when I plug it into the calculator, that I actually calculate. However, the problem may ask you for this angle. And we all do it, which is why you get multiple attempts at WebAssign. We all do it. We go ahead and plug this in and we figure out, let's say that this is 36 degrees, and we plug in 36 degrees and WebAssign goes, eh. Because WebAssign wanted that angle, and that angle is 180 degrees plus my 36 degrees, and that gives me 116 degrees, if I've done my arithmetic correctly. So you got to be careful about how the problem is worded, because you've done everything correct here. You just didn't provide the answer that WebAssign was looking for. You had to take it one more step. So that's why you want to kind of make sure that we're dealing with those things correctly.
$116 degrees.
180 plus 36, did I add it wrong? Oh, thank you.
Yeah, you
No,
wrote,
that's
you
180
wrote
degrees.
116.
216, okay, yeah. Yep, like I said, if I did my arithmetic correctly. And if that, I'll tell you what happens. If I gave you 116 degrees and 216 degrees multiple choice, and you clicked off the 116 and you show your work, you're going to get most of the credit for the problem. Because we all know we make arithmetical mistakes. And sometimes I have seen people that have written everything down to the right step and get some weird answer, and you're going, I don't know what buttons you pushed on the calculator. Because that answer is not there, and everything up to that point is, and so you'll get most of the credit for the problem. Okay, so let's talk vectors. So we just already said vectors have direction and magnitude, right? So there's my vector, it has direction and magnitude. Now, this morning it wasn't so bad, but yesterday afternoon, if you were driving between Tonkawa and Ponca City, and if you took your hands off the steering wheel, you were going to end up in the ditch. Because we had a very strong south wind. Okay, we had a really strong south wind. If I am flying and I have a strong wind that comes in and I have a strong wind that goes like this, the actual direction that the plane is going to fly in is going to be a little different. And we know this. So for example, if I have a river here and the river is flowing this way and I'm taking my little motorboat across this way and I'm trying to go straight, we know that the motorboat is going to land down here somewhere, right? It's actually going to go in this direction. Because I am doing this, I have what we call vectors. They have direction and magnitude, and I can add them head to tail. I can actually add them head to tail. So we do this all the time, right? We do this all the time. I've got city blocks. So I'm going to give myself some city blocks here. So we're going to say our person walks over 4 blocks and then walks up 3 blocks and ends up at a point there. But if I'm looking at where I am from this point over here, that's that right there. This is vector A, and I'm going to use the A with the little symbol over the top. That tells me it's a vector quantity, and this is vector B. And I've got my vector B there, and this is my resultant vector R. And in this case, we know the magnitude of R because if this is 4 blocks, and this is 3 blocks, I'm going to have 4 squared plus 3 squared is equal to 16 plus 9 is 25. That's going to give me R is going to equal 5 blocks. So I've got the magnitude, and if I want to represent magnitude, I usually use an absolute value sign to represent magnitude. We can calculate that, and I've added my vectors head to tail. Now let's start here. And we're going to travel south 2 blocks. And we're going to travel east 2 blocks. And we're going to end up over here. So this is the new spot. We've got a new R. And now I've got a vector B that is a negative 2 blocks. I'm going to call this B prime on my picture. We'll call this A prime on my picture so that we have that. So vector B is a negative 2 blocks. Vector A is a positive 2 blocks. My vector R, the magnitude of my vector R is going to be that 2.82 because it's going to be, this is going to be 4 squared plus 4, or 2 squared plus 2 squared, which is 4 plus 4, which is going to give me 8. And the square root of 8 was like 2.82. The square root of 8 is equal to 2.82. That gives me the magnitude. But look at the direction of my vector. Okay, my vector is going down, and this one was going up. So we utilize, and you guys have seen this before, and I probably taught general physics here in Takwa or here at NSC for a couple of years, about 3 years before I realized that your algebra book never actually says vector in it. Never uses the word. So, so I've expected you all to know that vectors have never used the word, but it has used vector notation. So in this first case, vector A, which we said was 4 blocks, but it was 4 blocks in the I direction. I is a unit vector in the x direction. J with the little hat is going to be a unit vector in the y direction. And if we ever get into 3 dimensions, k is the unit vector in the z direction. So when I did this, if I'm doing 4 blocks, this first vector here can be written just like that. Vector B is written, and I'm doing this over here for a reason, is in the j direction, because I did 3 blocks in the j direction. Now, if I were writing this in Cartesian coordinates, we know this is x and y, and we know this is going to be 4, 3, if I were writing its points. And it turns out that I can do this mathematically as well. This becomes 4i plus 3j. So I've written this vector in vector notation for a vector that we've described a little differently. The magnitude of this is going to be 5. Just like what we did right here. 4 squared plus 3 squared gives me 25. Take the square root of 25 and I get 5. I added these vectors graphically here. This is adding it graphically. I added it mathematically over here. So I'm going to do the same thing this time, but I'm going to do it with our second one. Our second one, our vector A prime, was 2i. My vector B prime was minus 2j. My vector R was 2i minus 2j. And we could calculate the magnitude the other way. I added these vectors graphically. And I came down and I added them mathematically here. So I'm going to go ahead and put a line in here so this looks a little better, because we're all used to those little lines. And I added them mathematically. Now this becomes very important. And we're going to see that get important week after next, when we start dealing with motion in 2 dimensions. It's really important because motion is independent in the x and y directions. And when the guys that did lab on Monday, remember when we were doing the basketball shoot? The video analysis of the basketball shoot, which is one of the reasons why I have you do that. We got one line that looks like this. And this is the y direction. And we got one line that looks like this in the x direction. But it was the same basketball. But the behavior in the y direction and the behavior in the x direction are different. They're independent of each other. And we have to be able to account for that by separating out the components of the vectors. So we're going to get that, and it's going to, as we start working with it, it's going to become a little clearer, but we have to introduce those vectors so that you know how to use them right now. Other things. So I could have a vector that goes like this, and we talked about the wind, so I can add it like this, and so I can put in, so I can do this graphically. You know, I don't have to have everything, and you know, everything's just not x and y like I do with right triangles. I can add them graphically. I can bring a third vector in, and my resultant vector is going to be this right here. This is my resultant vector, because I'm adding everything head to tail. So I can do it graphically, which is one of the reasons drawing a picture is really important, because you want to make sure that things are making sense. Okay? So when I add vectors, my resultant vector, I'm going to add vectors A plus B. So that's the mathematical determination of everything. I can subtract vectors. So I can take a new vector, R is going to equal A minus B. And basically what will happen is I will take the minus sign over my B vector and do it that way. And let's kind of play with it a little bit. If I am doing vector A, I can actually represent this as AX in the I plus AY in the J. And my vector B is equal to BX in the I plus BX in the J. And my resultant vector, if I am adding these, this is going to be AX plus BX in the I. This is going to be AY plus BY in the J. If I'm subtracting, this is going to be a minus BX minus BY. And that's my resultant vector is going to be AX minus BX I plus AY minus BYJ. Now if I'm using these, and now I'm going to do A plus 3B is going to equal something. This is going to be A is equal to AXI plus AYJ. And I'm going to do 3B. This is going to be 3BX plus 3BY. And so now I'm going to get AX plus 3BX in the I direction plus AY plus 3BY in the J direction. And that's going to be my resultant vector. And I know you guys have had it. Okay, I know you've had it. Just that they didn't call it vectors. And I know you had it because I actually have several of you that will give me some interesting notations. And I'm going, okay, I haven't seen that one in a while. But you've seen it, just that your algebra book never called it a vector. And what happens is we can now take the components, we can now go backwards. I still see people writing. Do I need to wait just another couple seconds? Okay. I'm seeing deep breaths now. I'm seeing deep breaths now. Okay, we good? The other beautiful part is get the recording uploaded. You know, you got that out there. All right, so what we're going to do is we're going to fly in an airplane. So, and everybody is going to learn that my artistic ability is a little limited here. So here's my airplane. We're going to fly my airplane in a northeasterly direction for 300 miles. So basically, I'm going to have a vector that's going to be 300 miles. And we said it was northeasterly, but I'm going to go ahead and say that this is 47 degrees. After 300 miles, the pilot's going to make a turn. And we're going to turn more easterly. So we're actually going to do this. So I've got my vector up here. And we're going to fly another 500 miles. And in this case, this angle is going to be 25 degrees. And then we got to deviate from a thunderstorm. So now we're going to make another turn, and we're going to come down here and go 200 miles. And we are going to be at 50 degrees. And this is X marks where we're landing. I want to know the resultant vector, because this is going to be a vector problem. I want to know, and this actually is going to have a special term that we'll talk about on Friday. This is going to have something called displacement. But I want to know the direction and magnitude of this resulting vector. Okay. I can do this a couple of ways. I can do this graphically on a piece of graph paper and use a protractor and come in and measure it. Might be a fun exercise to do if you want to do it. But I am actually going to write out each of these three vectors in their component form. So we're going to call this vector A, we're going to call this vector B, and we're going to call this vector C. All right. If I do this, let me get my other pen here. So this first vector, I've got the angle and the hypotenuse. So vector A is going to be, for this side here, the x side, it's going to be 300 cosine 47 degrees in the I direction. If I go back and look at my triangle, there's my triangle, there's my cosine, here's my angle, it's the adjacent. This is what I'm looking at, and I'm writing it down in its vector components. My B side is going to be 300 cosine 47 degrees in the J, or not cosine, sine, sorry. Sine of my angle in the J direction. My B vector, I'm going to do the same thing. 500 miles cosine 25 degrees in the I direction plus 500 sine 25 degrees in the J direction. And my C vector is going to be 200 cosine 50 degrees. But it's going to be negative because it's going in the negative y direction here. So if I'm drawing my triangle that you guys can see it, drawing my triangle, this is in the negative direction. So that's going to be 200 sine 50 degrees in the J direction. So now for my resultant vector, I'm going to add up the 300 cosine 47 degrees plus 500 cosine 25 degrees plus 200 cosine 50 degrees. That's all going to be in the I direction. And now for the J direction, it's 300 sine 47 degrees plus 500 sine 25 degrees minus 200 sine 50 degrees in the J direction. Now I get out the calculator and do the arithmetic. So 300 times cosine of 47 degrees. And I like to kind of keep track of my numbers to make it easier for me to figure out where I might have made a mistake. So that's 205. This is 453. And this is 129. So I'm going to add all those together. This is going to give me 787 in the I direction. Now we're going to do the J direction. 219. $211. $153. This is going to give me minus 153. Gives me 277J. Just so you know, I use a Latin 7. It helps distinguish between a 7 and a 2, and some nice, it just makes it clearer when I'm writing on the board to use the line through the 7 to make sure it's just not a squiggle or something like that. So that's why I use a Latin 7. So that gives me the X and Y components, and if I want to find the magnitude of that, that's going to equal the square root of 787 squared plus 277 squared. Gives me 834 miles. And if I want the angle is going to be the arc tangent of 277 divided by 787. And that's going to tell me that that is 19.4 degrees. So I can go back and forth between my vector notation and my graphical notation. I can go back and forth between my X and Y components and give you its magnitude and direction in terms of an R and an angle. And we will be utilizing that quite a bit. Making sense? Kind of remembering it from that weird section in algebra that you had no idea what you were doing? Because we're putting things back to having physical meaning. You guys good over in Enid? Everybody good online? Other questions? Okie dokie.